In lecture 10, we're still going to discuss hypothesis testing, but we will focus on two sample tests. Okay, so in lecture 9, we learned one sample test. H0 is always mu equals mu 0, which is an assumed population mean. So the alternative hypothesis could be that mu is not equal to mu 0 for two-sided test, or mu is larger or smaller than mu 0 for one sample test. For two sample tests, the null hypothesis is that mu1 equals mu2 because we will have two groups here, which means there will be two populations and two samples. And the alternative test could be that this two population means not equal to each other, or one is larger or smaller than another one. Okay, so more details here. So now we have two groups, X1 for group 1, X2 for group 2. We have two populations with two means and two standard deviations. Of course, eventually we have two samples. We have two samples, and for sample 1, there is a mean value, X1 bar, a standard deviation, and sample size. For sample 2, it's similar. So objective, two sample test is for difference. It's for the test for difference between population means of two groups using two independent random samples, which means that these two random samples drawn from two groups, they should be independent from each other, which means that when you created them, they should not, the method should be independent for each one of them, which means that they did not affect each other when observations were drawn, when samples were formed, okay? And we also need to assume that each population or each group here is following normal distribution. And if we know population variances for these two groups, then good. If we don't know population variances, we need to assume that they are equal to each other or not equal to each other. And the population variances, assumption on population variances is very important. We'll say that later. So we're still going to do t-test or z-test. If we know population variances, then good. We use them. We use standard deviations of population 1 and population 2 to do z-test. If we don't know them, we don't know population variances, we use standard deviations of two samples to do t-test. Okay, and the statistics, they changed a little bit. For z-test and t-test, numerator is the same. Okay, it's simply the difference between two means from two samples. The denominator is different. Now we have sigma and sigma cap. And they are not about any sample here. They're about a new data set, which is following, also following normal distribution, I can tell you that. But this new, say, data set is a poor data set addressed by the difference between two means from sample 1 and sample 2. Okay, so we have assumed that two populations or two groups, they are the same thing. X1 and X2, they are both following normal distributions, right? With mu1 and mu2 as means, sigma 1 and sigma 2 as standard deviation. So according to the CLT, that poor distribution between X1 bar and X2 bar is also following normal distribution with a mean addressed by the difference between mu1 and mu2, and a variance addressed by sigma 1, sigma 2, n1, and n2. Okay, so this part, mu1 minus mu2, is for the mean of the poor distribution, of the poor data set. Okay, see that. And the second, the more complex formula here is for the variance of the pooled data set. So this normal distribution here can be considered as a pooled normal distribution. It's still normal distribution, it's just it's a pooled one between two samples. And the null hypothesis is mu1 that is equal to mu2, the population mean of group 1 equals the population mean of group 2. Okay, if H0 is true, then for this pooled distribution, it has a mean value of 0. And the variances here stays the same. Why is it 0? Because it should be the difference between mu1 and mu2. And if mu1 equals mu2, then it must be 0, right? Because we assume that H0 is true. So for test statistic, if we know variances of two groups, then it's very straightforward. T-test is addressed by this formula. Numerator is the difference between means. Denominator, you just need to use this formula, right? This formula, this part of the equation is just this, right? But you need to calculate the square root of it, because here it is variance. Here is a standard deviation. Standard deviation is the square root of variance, right? So since you know sigma 1, you know sigma 2, sample size, you know n1 and n2, you also know means, then just calculate the z-test. But if you do not know population variances, unknown, then you need to use t-test, and you need to calculate something called sigma cap. Okay, you are talking about using t-distribution instead of standard normal distribution. So t-statistic here, I showed you this formula before, but the tricky part is the calculation of sigma cap. Why is it tricky? Because you have to assume if variances are equal or not equal to each other, because we don't know them, right? That's the reason why we use t-test. And beyond that, we don't know them, we have to assume if they are equal to each other. If they are equal to each other, then you need to use this formula to calculate sigma cap. It is about N1, N2, that's something you know. And SP is a pooled standard deviation. It's about N1, N2, and standard deviation of sample 1 and standard deviation of sample 2. So we don't know variances, then t-test. And after that, we're doing t-test, but you still have to assume if these unknown variances are equal to each other or not. If they are equal to each other, calculate SP, then calculate sigma cap. If you assume that these two unknown variances, they are not equal to each other, then the calculation of sigma is straightforward. You don't have to calculate SP. You simply use S1 and S2 to calculate the pooled standard deviation, okay, sigma cap. So now you know the importance of variances, right? If you know them, population variances, if you know them, then you use z-test. If you don't know them, you use t-test. But before that, you still have to assume if these unknown variances are equal to each other. If yes, calculate SP first, then sigma cap. If no, simply use S1 and S2 to calculate sigma cap. And also, if your sample size is large enough, say we have two samples, both of them have a sample size larger than 30. If that was the case, t-distribution is very close to standard normal distribution. Then you can simply use z-test. Of course, you can stick with z-test, right? But if these two samples they're big enough, you don't have to use t-test. Simply use z-test so that you don't have to consider if these two unknown variances are equal or not equal to each other. So that's a shortcut. Okay, so this is something you may face in future in your research or in your work, right? And in the exam, in practice, in the book, specific questions will ask you, will give you very clear information about using t-test or z-test. For example, the information about variances, and then you have to decide based on specific requirement from your questions, right? But if your sample sizes are just large enough, you can simply use z-test, even that you don't know variances. Okay, and of course, when you are using t-distribution, nu is something you always need to figure out, which is the degree of freedom. For one sample test, degree of freedom is simply n-1. But for two sample tests, it's still tricky because of, again, variances. When you're doing a t-test, it already means that you don't know variances. And here you still have to make assumptions. If you assume that these two unknown variances are equal to each other, then the degree of freedom should be n1 plus n2 minus 2. If you assume that these two unknown variances, they are not equal to each other, you need to find the smaller one between n1 minus 1 and n2 minus 1. Use that smaller value as the degree of freedom. So you can see here, assumption about variances is very important. Equal, not equal. So here, let's just show some decision rules. You can see that they're basically the same as before, as one sample test. But for t-test, it's a little bit different, okay, because of the degree of freedom. So let me draw this again. You can simply use the same graph to decide, okay? So for example, this is horizontal axis, this is a vertical axis, right? And let me draw, say, I simply use this curve to represent standard normal distribution and t-distribution, okay? Because they are very similar to each other. So you have z-test value, you have z-half alpha value for critical value, right? Say, for example, this is where you have negative z-half alpha. This is where you have positive z-half alpha, right? These two critical values decides boundaries of reject or not reject zones, right? These two dashed lines. So the zone between them is for not reject. The zone to the left and to the right of them, these two zones, they are for reject zones, right? So if your z-test value is on the right side of your z critical value somewhere here, then you reject. If your z-test value is negative and it's on the left side of minus z-half alpha value, it's still reject. But if your z-test value is somewhere within this range, then you do not reject. Right? This graph works for one sample test, two sample tests, no matter z or t. Okay, so simply memorize this graph and draw it for yourself when you're doing exercise or finishing homework or in the exam. Okay, for z-test, it's more complex because of this assumption of variances. Because if you have different assumptions, you have different methods to calculate the degree of freedom for t, which means that when you are using t-table to look up critical t values, you have different degree of freedom values, right? That's the reason why the lower decision tree here is a little bigger than or larger than the z-test decision tree, but it's all about degree of freedom, okay, for two-sided test. for one-sided test, it's similar. It's similar. You can still use this graph, right? And what you need to do is still comparing test values, no matter z-test values or t-test values, with critical values, no matter z critical values or t critical values. And when you are trying to look up t critical values, okay, be careful with the degree of freedom. We're doing two sample tests now. Degree of freedom could be n1 plus n2 minus 2. Could be the smaller between n1 minus 1 and n2 minus 1, depending on your assumptions on variances. Okay. This is exactly the slide I showed you in the last lecture, right? These 6 steps, they stay the same, right? Even though we're talking about 2 sample tests. Okay, and okay, I will simply use one video to finish this lecture, because we're going to discuss 2 examples, and they're actually very straightforward. Okay, these examples, they are for 2 sample tests, of course. So suppose we want to know whether differences in the annual swimming frequencies exist between the central city and the suburban regions. Okay, we have 2 groups, central city, suburban regions of a metropolitan area. Okay, so we interviewed 8 individuals in each region and collected the following data. So for central city, 8 people here. Okay, for suburbs, we have 8 people, and each one answered about their frequency, for visiting swimming pools, right? So, for example, this individual 1 from Central City said he visited swimming pool 38 times. So 1, 2, 3, 4, 5, 6, 7, 8. Interviewed 8 cities from Central City, and other interviews, and other 8 individuals from suburbs. Okay, and we have 8 samples, because each sample contains 1 person from Central City and 1 person from suburbs. But yeah, we have 2 groups, Central City, suburbs. And for each group, because 8 people obviously is not the whole city, is not the population of Central City or population of suburbs. So we have 2 groups for actually 2 means for 2 groups, right? That's a correct way to address this. So the mean for Central City is 48.63, and the mean for suburb is here. The standard deviation for group 1 is here. Let's say sample 1 is here. For the sample of group 1 is here, and a standard deviation for the sample of group 2 is here. Okay, step 1, null hypothesis, mu CC equals mu sub. CC central city, sub suburban. We're going to do 2-sided tests, so alternative is that they're not equal to each other. So step 3, choose the significance level. Usually, this value should be provided by the question. Again, in your research, in your work, in future, you can decide it yourself, but let's just say 0.05, okay, for this example. So choose the test and find Z or T test values. Since the population variances are unknown, because nothing was mentioned about variances, right? And the sample size is small, variance is unknown, we use t-test. Okay, let's just assume equal variances. And if you go back to find out the formula for SP, it's about standard deviations and the sample sizes, okay? And you can calculate the value, 16.67. And then you you just follow the formula for eco-variances t-test. You find out that the value is 1.8. Okay, so what's the critical value? What's the critical value? So because we're doing two-sided test, right? So we need to find out t half alpha with a degree of freedom of n1 plus n2 minus 2. Why? Because we assume equal variances, right? So this is a degree of freedom. So you look up the t table, you find out that the critical values are positive and negative 2.14. So test value 1.8, smaller than what? The positive critical value. Then we know that this t-test is within the not reject zone, so we do not reject the null hypothesis. What's the null hypothesis? What's the null hypothesis? There is no difference in the mean swimming frequencies between the centricity and the suburban region. Okay, so the tricky part could be here, the calculation of SP and the calculation of t-test value. You have to be very careful, okay, in order to not make mistakes in calculation. So about the selection of tests, we don't know variances, then it's t-test, and the sample size is actually 8. It's still t-test, it's small sample, right? About SP, this is based on this assumption. Usually, this assumption should be provided in the question if variances are not known. So here we just assume they are equal. If we assume that they are not equal, then we don't even have to calculate SP. We simply use S1 and S2 to calculate t-test, right? Okay, so next question, next example. So it's a modified example of the one we used before. So here, let's just suppose we modify the previous example by assuming unequal variances. Like I said, simply use S1 and S2. You don't have to calculate SP anymore. So the rest steps, they're the same, step 1 to 3, right? So the t-test here is different. You have S1, S2 instead of SP. Simply replace this these parameters with specific values, then you should have a result 1.8. And then you have to just find critical values again, because the degree of freedom is different. Because now we're assuming unequal variances. You have to calculate n1 minus 1, n2 minus 1, and use the smaller one as the degree of freedom. Okay, then use t-table to find out critical values. You'll find out that this time critical values are positive and negative 2.36. But still, 1.8 is smaller than it, which means that you should not reject. Okay, so 1.8 is the t-test value for the second example. Yeah, conveniently, 1.8 was still the value for the first example when we assumed equal variances. You should know that this is just a coincidence, okay? It is not saying that t-test value is the same, no matter you assume equal variances or not. You still have to calculate SP if it is equal variances assumed, and then have t-test value. If you assume not equal variances, just use this formula to actually calculate t-test value. Here, two values, they are both 1.8, it's just a coincidence. Okay, so yeah, that's all I want to introduce for this lecture. You can say that the two sample test is just an extension of one sample test. there is difference in terms of the calculation for t-test value and z-test value, okay, compared to one sample test. And here you also need to be careful about assumptions on equal variances or unequal variances, because this assumption decides the calculation of sigma cap, thus affect the calculation of t-test. And it also affects the selecting of degree of freedom, right? So, yep, that's it. Okay, and like I mentioned before, find some solved tests from your solved questions, solved problems from your textbook, and try to solve them by yourself. Or simply just solve these two examples I provided in slides and compare your results with results provided here and do some practice and you will be good. Okay, thank you.